So
Okay, hi everybody. Okay, welcome back everyone to the next session. I'm going to get us started because we're running a bit behind. I hope you enjoyed coffee. Firstly, an announcement. At the end of this session, we're going to be doing the conference photo, which will be at the front of the building. So just come out and turn left and we'll stand on the steps and get the photo done just before lunch. Okay, so this next session is all going to be moving up into the high redshift universe, and we're going to be started off by Adelaide Clessance, who's going to be talking about resolving star formation region, high redshift and lens galaxies with our wonderful JWST. So over to you, Adelaide.
thank you. So my name is Adelaide Clessance, and as you can hear, I'm French, but I'm working in Sweden in Stockholm University with Angela and Damo, and also with Matteo Mesa, who will do the next presentation. So I will present James Webb results on clumps analysis in high redshift galaxies. So as we know, thanks to HST, the high redshift galaxies are dominated in their morphology by clumps. But with HST at high redshift, we can only resolve kiloparsec size or 500 parsec size clumps. So one way to overcome this resolution limitation is to use gravitational lensing. Thanks to the gravitational lensing, you can observe magnified background galaxies and zoom in within the galaxies and detect smaller and fainter substructures. So you have one example here of a HST observation of a lens galaxies, and all the clumps that you can see here are hundreds of parsecs in size and not kiloparsecs. And it's even better if you can combine James Webb with a lensing effect, because you can detect thousands of very faint, low mass and small clumps. So I can show you, if I switch from HST to James Webb for this galaxy, we can detect more clumps, fainter clumps. We can split some HST clumps in multiple components. It's the same here. If I switch from HST to James Webb, we detect really more structures. And in this galaxy that we don't detect with HST, if we switch to James Webb, we detect two images of the same galaxies with very small clumps, which are actually star clusters size at redshift 5. So in order to build statistical samples of this kind of clumps, we focused on the James Webb observation of one lensing cluster, which is called Abell 2744. So that it's a NIRCam images of the cluster. It's a very massive cluster producing a lot of lensed objects in which we can detect clumps. So before to continue, I will just take 1 minute to explain what we call a clumps as observers. So for us, a clump, it's an observational entity, so it's a compact and bright substructure detected within a galaxy, like this one, for instance. And then depending on the physical resolution that you can reach, which depends on the redshift and the magnification, it can be a lot of different things. It can be a satellite galaxies, it can be a large star-forming region, it can be smaller star-forming regions, and if you have very high magnification, you can break down to star clusters, individual star clusters at high redshift. And then what we call a clumpy galaxy. So for us, a clumpy galaxy, it's a galaxy with at least two clumps, two compact bright structures. And in the observation of Abell 2744, for instance, we have a lot of non-clumpy galaxies like this one. You don't detect any clumps or just one, and a lot of very clumpy galaxies like this one. So I show here a subsample of clumpy galaxies from Abell 2744 from redshift 0.7 to redshift almost 10. And you can see that we have a lot of different types of galaxies, different inclinations, different colors, different morphologies, different redshifts. So it's a lot of different things in the same sample. So we selected 484 galaxies from the observation with at least magnification around 2 to get the zoom in, the boost in the resolution from lensing. redshift between 0.7 and 10, and in order to build a large sample of clumps, and we have 35% of spectroscopic redshift from use or for James Webb spectroscopic redshift estimation. You have here the number of clumps per galaxy as a function of redshift, and I draw a line here because what I will present today is the results of the clumps between 0.7 and 5.5 in redshift, so post-reionization clumps, let's say, and we will do another study with Angela Adamo on the very high redshift clumps. In total, we have 2,004 individual clumps, and it's 10 times larger than the first sample that we did with James Webb, which was based on the SMACS 0723 observation, so the very first observation of James Webb. So why do we want to study clumps? So we know, thanks to the HST works and also simulation works, that clumps are in the distant galaxy and they can affect the evolution of the galaxy, and we want to understand how do they form and how do they evolve in their host galaxy. On the formation side, we have two main scenarios proposed. It's in situ formation from gravitational collapse in a gas-rich and a turbulent disk, or galaxy mergers. Then on the evolution side, we know that clumps can be affected by feedbacks, mergers, tidal force, and can migrate within the galaxies. And all these parameters will affect their survival timescale, and most of the simulation says that they should not be able to survive longer than 300 to 500 million years. Then if they migrate within the host galaxies, they can also participate to the formation of bulges and structures within the galaxies. And the last thing that we want to study is that they are found to be a high star formation rate and very high density, so they could be the site of star formation within galaxies and young and globular clusters formations. So it's what we want to study with this sample. So Abell 2744 has been observed with all the broadband and all the medium bands from James Webb. So it's a lot of data on the same clusters. So you have one example here for this clump in a galaxy at redshift 2.3, where you see all the detection in all the filters. And because we have this combination of broadband and medium band filters, we can constrain for individual clumps the strength of, of some emission lines depending on the redshift, which help us to get a reliable age, star formation rate, and so on from a simple SED fitting process with short star formation histories because they are compact objects. So I will not show everything because I don't have time in 10 minutes, but I will show the main results of the soon submitted paper. So I show here the size of the clumps in 4 different redshift bins with almost the same quantity of clumps in each. So we have clumps from below 10 parsecs to 600 parsecs. We don't have any kiloparsec size clumps in this sample. And we find that the higher redshift clumps are on average a bit smaller than the low redshift, which for me low redshift it's 1, 2. Then if we go to the age, so we find age between 1 million years to a few gigayears in the low redshift galaxies from the sample. And we have, of course, older clumps in the lower redshift galaxies. And what is interesting here is that we have 10% of clumps with an age higher than 300 million years and 8% higher than 500 million years, which was the limitation of the simulation. So the clumps should be able to survive, at least some of them, to older ages. And we can compare then this distribution with some simulation to understand how they can survive longer than what we expected before. Then we have masses of the clumps, so we delens the mass with the lensing magnification, so we have masses between 10 to the 5 to 10 to the 9. It depends on the redshift also, and what I show here, it's a cumulative distribution of the clumps mass in the same 4 redshift bins that I showed before, and what you see is that the cumulative distribution is very stable with redshift. It's really similar, and also it's consistent with a power law with a -2 slope, which is what we expect if the clumps form for fragmentation. We would expect this type of cumulative mass distribution. So it's a good, it supports the in situ formation scenario for the clumps. So then we have also the properties of the galaxies. So we can try to understand if there is a link between the clumps properties and the host galaxy properties. So I show only one plot of that sphere. So it's a fraction of mass. So it's the sum of the mass of all the clumps divided by the mass of the galaxy. So to understand which fraction of the mass of the galaxy is within the clumps. And it's with galactic mass and color-coded by specific star formation rate of the galaxy. And what we see here is that the lower mass galaxies, like below 10 to the 8, are very active in star formation, and most of their mass is within the clumps, while for higher mass galaxies, which are also the lower redshift because of galaxy evolution, they are less active in star formation rate, star formation and lower fraction of the mass within the clumps. So a significant fraction of the star formation is happening within the clumps, especially at low mass galaxies on a bit higher redshift. And then the last thing that we try to do, is to understand if there is a link between the position of the clumps within their host galaxy and their properties. So we measured the galactocentric distance of the clumps from the center of each galaxy in the source plane to get a physical value. And what I show here is a fraction of mass, so it's a mass of each clumps divided by the mass of the galaxy, with the galactocentric distance in the same 4 redshift bins. And what we see is that the central clumps are on average more massive. For the more evolved galaxies, like the 2 first redshift bins, we have some bulges, also proto-bulges, so of course they are very, very massive in the center of the galaxy. So it can say that even the clumps maybe can migrate, and during the migration they can grow in mass or merge together, or also maybe in the center of the galaxy, if clumps form there, they are formed with a higher mass from the beginning. And then we did the same exercise with the age, because the simulation said that if there is a migration, we should observe an age gradient of the clumps within the galaxy, that we don't. On average, we don't see any age gradient with the galaxy on average, and we don't see it really on individual galaxies also. So we have old and young clumps more or less everywhere within the galaxies. And the last things I want to show is that, as I said before, if you have very high magnification, you can detect individual star clusters. We have some of them in the sample of Abell 2744, and we have some of them from other observations, like this one. So we detected, we confirmed individual star cluster from redshift 1.4 in the Sparkler galaxy to redshift 10 in the cosmic gem arc that you have here. So it's quite a recent paper. So we start to collect high redshift star clusters that we can study. And then for later, we will continue to study that with new data. So we'll get the glimpse data, very, very deep NIRCam data on one cluster. It's cycle 2, it will come soon. Then we are getting now a NIRSpec IFU and NIRCam data on 3 galaxies, including this one, redshift 5 galaxies with a lot of clumps. So it's led by Johan Richard. And then we will get also in cycle 3 NIRCam images of this cluster, which produce very, very high magnification. And we are getting also Muse images, Muse data cube, the same cluster at the same time. And Angela Adamo is leading also NIRSpec IFU observation of this specific galaxy, which is in Abell 2744, to study the clumps in this face on almost spiral galaxy at redshift 2.6. And thanks for your attention.
Thank you very much. Any questions for Adelaide?
Thank you, Adelaide. Very nice talk. So when you measure the sizes of the clumps, are they at the same rest frame wavelength? Or is that the same observer frame wavelength? Because you go from redshift 1 to redshift 5.
So we have one reference filter for each galaxy, which is, so we change with redshift. So we have 3 different reference filters. So it's between 115, 150, or 200 in James Webb. But we don't really use the long wavelength filters because the resolution is a bit less good. So it's not exactly the same rest frame wavelength, but we change filters with redshift to try to get a similar rest frame wavelength.
Thank you.
Great talk. You mentioned that the properties of the clumps could help be directly compared to models to constrain feedback. Could you say a little more about that?
Yeah, so actually it's a bit difficult to do it directly because the definition of a clumps in the simulation, it's not the same as the definition of a clumps in the observation. As for us, clumps is really an observational entity, like we say that's a clump, and then we observe it, we characterize it, and then we know what it is at the end. So it's a bit difficult to do it directly, but what some simulation predict is that, for instance, the densities that we find, which can be very high, in the simulation, they are directly linked to the feedback recipes and feedback strengths that they put in the simulation. So they are able only to produce very dense clumps with some specific recipes of feedbacks. So we can try to compare a bit that, but it's a bit difficult because of the different definitions of clumps.
Okay, one last question.
Hi, nice talk. So in the plot where you showed the fraction of the galaxy mass in clumps, some of the points were above 1. Could you touch upon that, please?
So yes, we have a line here, which is 1, and sometimes we have a mass of the clumps, which is higher, which is weird. So we believe it's a SED fitting issue because we are fitting the galaxy with everything, and then we are fitting the clumps. So we would like really to, in the next studies, to study the impact of the clumps on the star formation history of the galaxy when you do SED fitting. So we would like to fit the clumps, to fit the galaxy, and to fit the residual light when you remove the clumps from the galaxy to try to understand this effect, because we are biased a bit.
Okay, well, thanks, Adelaide Cossens again. And next up.
That's great. Yeah, nice.
So next up we have Matteo Messa from INAF, who's going to be talking about parsec scales at Redshift 6 star forming system with NeoCam and NeoSpec.
Thanks. Hello, everybody. So yeah, I will keep on discussing why it's interesting to study high redshift galaxies down to the smallest possible scales. One of the reasons that probably was not mentioned yet is that at increasing redshift, what we observe is that there's an increasing number of galaxies dominated by line emission, so that either have young stellar population or bursty star formation histories. And this is linked to large equivalent width. I'm showing a distribution redshift around 6 of equivalent width, H beta plus of 3. And we also see that large equivalent widths are linked to efficient production of ionizing radiation. So we may wonder what's the source of this line emission in this kind of galaxy. Because on the other hand, at low redshift, we observe that when we have starburst galaxies, their recent star formation is mainly within clusters. So here I'm showing an example, this ISO 338. In this galaxy, 50% of the very recent star formation is within star clusters. So we're trying to investigate these also at high redshift, so providing this link. And we saw that one way is via gravitational lensing. It's been already discussed, so I can already skip directly to my target. So time is short, so I decided to focus on just one system, which is in this galaxy cluster. This is a Hubble's and James Webb release of data. And thanks to the MuseDeep field, we recognize a Lyman alpha halo at redshift around 6 in this galaxy cluster. Actually, not a halo, but some halos at the same redshift. Actually, basically, there's a main one where magnification is above 15. There are a couple of counter images of that. And then there are other halos which are same redshift and separated by tens of kiloparsecs. And already with HST, it was clear that behind this Lyman alpha halo, there are very compact UV sources. There are 3 main ones, which is the one I'm showing here. And what I'm presenting now is a study based on NearSpec IFU data from this Cycle 1 program led by Eros Vanzella, plus NearCam from the Canox and the Canox and Peirce team, sorry. And this is my main slide. So I want to convince you that despite the fact that I'm presenting just one system, it is still very rich with information when we get down to the few of parsec scales, because what we observe are dense star clusters, compact regions of emission, of extreme emission lines, possible Lyman continuum leakers, and extremely metal poor region down to few % solar. So now the rest of my talk would be trying to convince you of that. First of all, compact star clusters. So with NearCam observation, it was clear that if we look at these UV sources, they are characterized by the presence of few very compact region which has unresolved even with James Webb. And this is true for all the sub-region in this main system. And if we measure their sizes, thanks to the gravitational lensing, we're getting down to 3 to 8 parsecs. So these overlap with the sizes of clusters in local galaxy, which are the red points in this plot. And we can also derive masses and density. So the masses of these clusters are around 10 to the 5, 10 to the 6 solar masses, and density around 10 to the 3 to 10 to the 4 solar masses per parsec square. So we are a bit, confident that these are genuine individual clusters and they are slightly denser than what we observe in local galaxies, which is consistent with what's been observed in other magnified systems at high redshift, which are the black points here and the color points. And not all the clusters have the same ages, for example. Here I'm showing an example. These 3 clusters here, we don't see any emission lines. And indeed, when we do SED fitting, we find ages around 15 million years. And if we compare the age with the crossing time expected for these sources using their density, it looks like these should be gravitationally bound sources. So they survive their initial phase of formation, so they may evolve to become possibly even globular clusters. Now, moving instead to line-emitting sources. So in this region here, we see actually some line emission. If we took this source unlensed, we would have seen something which is minus 18 UV magnitude, 10 to the 7 solar mass, more or less, 10% solar metallicity. That would be one of the, I guess, typical line-emitting galaxy that we're seeing now with James Webb at this redshift. But if we zoom in, so here I'm showing a map of the equivalent width for these sources, we see that there's a subregion which has equivalent width up to 3,000, so very high. Another one which has much lower equivalent width, but where we see also pockets of large line emission, which are the orange parts here. And so what we conclude is that possibly the production of ionizing emission comes from compact knots that are consistent with the position and the sizes of the single clusters we see. But that's not the end of the story. So here, in addition to the equivalent width maps, I'm adding UV slope maps. And the bluer the map, the bluer the slope. And for example, if we take this source here, so the cluster down here, this is the broadband SED. It's a line emitter, so we derive 2 million years of ages. And it has a very steep UV slope down to minus 3.1, which is so steep that we cannot reproduce with our model. So one possibility for that is that this is a leaker, because we know that if the escape fraction is non-zero, then the beta slope can be lowered down to values around minus 3. And if escape fraction is not 100%, we can still have some large equivalent width despite the escape. On the other hand, this other cluster up here, again, we see a very steep slope, minus 2.8, but in this case, we don't see any emission line. So the slope indicates that the population should be young, very young, but we don't see any line. And this is not the first case found. So for example, in the JADE survey, there has been found some galaxy with very blue slopes and no or very weak emissions. These are on galaxy scale. Actually, what we see is on the cluster scale almost, so very small. Again, the possibilities are either this is a leaker, so that's why we're not seeing emission lines, or that the so-called off mode of star formation. That means there was a burst of star formation that was interrupted, and now we're seeing this cluster exactly at the time where there are still enough massive stars to have a blue slope, but not enough or not massive enough to have the emission lines. Now moving to another subregion of the system. Here I'm showing rest UV and rest optical plus O3 and H alpha lines from NIRSPEC. And we recognize one of the two clusters that we already mentioned before, but also that there's a region which is completely dark in rest UV. That means it's very, very, it's very, very faint. So observed magnitude intrinsically is more than 31. That means this, we expect this region to have mass lower or not much higher than 10 to the 4 solar masses, but it's a strong emitter. And if we calculate what's the efficiency of the production of ionizing production, that's more than 26, so it's extreme. And to us, this is very puzzling. So we don't expect sources down to those masses to be able to have enough massive stars to produce this ionizing radiation. So any suggestion here is very much welcome. And again, that's not the end of the story. So this is the same source. And we recognize that there's a part of the galaxy, which is the red here, where we see both H alpha and O3. And if we compare them, we get a metallicity around few percent. But also there's another part of this emission where we see H-alpha, but we don't see O3. Again, if we compare them, we expect this to be very, extremely metal poor, so down to 0.5 solar or less. And this is not the only region metal poor, because even here, I've stretched a lot the colors, but there's a region which instead is barely detected with NIRCam. And again, we see H-alpha, we don't see, or it's barely detected DO3, so again, we expect metallicity down to 1%. And despite the fact that, again, this is low in stellar mass and very high in producing ionizing radiation. So these three are among the most metal poor regions we see kind of at any redshift, apparently. So now I don't have time to, time is running short here. I just wanted to say that this main region I was presenting, there's not much between them. So they're separated by a few hundred parsecs or some kiloparsec. And there's not much in between apart from this low surface brightness part here. And here's the position of the main sources in the source plane, again, separated by some few kiloparsecs. And we also see a shift in the position of the lines, so probably a peculiar velocity shift among them. So basically, I think what we're seeing here is satellite regions that are coming together probably to form a larger galaxy at redshift 6. And future work, Adelaide already mentioned those, so I will skip. And I go to the last slide. So I hope I convince you that even one single system, if it's studied at the smallest scales and with deep data, contains a lot of information. Thank you.
Thank you, Matteo. Any questions? Yeah, Brad.
Thank you. So locally, we're used to seeing some triggered star formation also in many cases. So I guess the question is, do you think you see anything like that, and how might that affect some of your analysis?
Some trigger star formation, meaning some,
Yeah, central object, 10 million years, around the edges, or next to it, 1 million years.
I'm not sure. The problem here is that, again, this is not, probably those are not, and most of them are not part of the same, there's not like a background galaxy and these are part of the same system. But, because initially we thought here, this part is quite young, this part here is older, so we thought that maybe something like that, or still something like the star formation process moving to within the galaxy, but distances here are really some kiloparsec away. So it's more something about interaction probably that is triggering the star formation.
Yeah, typically, 10 parsecs, 20, 30.
Yeah, this is very difficult to, on that scale, that's very difficult to see.
Very interesting talk. At the beginning, you showed this extended Lyman alpha emission. And I was wondering if you would look into the photon budget, into the relationship between the amount of photon available from the clumps and what is visible in the Lyman alpha, if there's anything missing, what is the fraction?
Not yet. Yeah, this is, maybe I forgot to say, but this is still work in progress. So, any suggestion is welcome, but we have in mind to do something like this, but we haven't done that yet. Yeah.
It's really nice data. Thanks.
So because you have the IFU, I was wondering, so what is the argument for having high F escape of 100% and having O3? And can you check that with your IFU data? Because you showed the 1D spectrum, right? And they didn't have O3 and there was H alpha for some of them. So I was wondering, is it because of some spatial effect in terms of the whole gas is ionized and everything is leaking, or is it more like channels leaking? Because if you want to tie it to the metallicity, it becomes a little bit more tricky to understand the ionizing conditions at the same time, right?
Well, I guess it's not, we recognize those two leaking regions, but again, on scale of single parsecs. We don't think they are maybe 100% leaking. That's why we're seeing overall, both here, we see actually the Lyman alpha halo and then the lines. Yeah, but maybe I didn't get.
So because you have the IFU, it's a spatial okay, is it smaller than a pixel is what you're saying? Is it the H alpha and the O3 kind of spatial distribution for these low metallicity? So
yeah, well, it's very difficult to compute a map in a sense. I mean, pixel by pixel, yeah, we thought something about it, but I mean, you have very low signal. So that's why we're going like more region by region in a sense. Yeah, especially, yeah, we're doing that spatially, yeah, let's say, but region by region, something on the like pixel or few pixel map scale that's almost impossible. I mean, we can do it, but we are dominated by noise. I mean, it wouldn't work. I wouldn't trust the result.
Okay, great. Let's thank Matteo one more time.
Hear me okay? Here's the pen. Cool. And laser point.
Okay, so our next speaker is Corey Perry, and we'll be talking about JWST emission line surveys. Thank you very much.
Perfect. So, hello folks, I'm Corey, PhD student at the University of Edinburgh, working with Philip Best and Ken Duncan, primarily on cosmic star formation, looking at star-forming galaxies over cosmic history with a multi-wavelength approach, but today I'll be talking about the work that we've been driving forward at Edinburgh, looking at JWST and probing emission line galaxies into the epoch of reionization in high redshift. So firstly, what is GELS? As the title slide alludes to, it stands for the JWST Emission Line Survey, in which my supervisor, Philip, is the PI of. It's a narrowband imaging survey using JWST filters, looking at in the Cosmos Candles field, where you can see the yellow kind of footprint in the image, and is 65 square arc minutes. And the lovely thing about where this is placed is Cosmos has got a wealth of multi-wavelength ancillary data from both HST, so from ACS and wide field camera, but also NIRCam from another survey that's led in Edinburgh called Primer, where we've got NIRCam and Mirror imaging as well. So what is it, the imaging strategy from GELS, and why are we doing this in the first place? So here we're looking at a combination of both narrowband and broadband imaging in both the short band and long band wavelength channels of JWST. The whole point of using these filter combinations is when we look at the spectra of galaxies, we look at the continuum emission, but we also look at the emission lines themselves. And particularly, we're looking to select emission line galaxies, and so what we can do is we can use the narrowbands to isolate the line emission from the continuum emission, thanks to either adjacent narrowbands or over-encompassing broadband, in order to select line emission galaxies over cosmic time. So the reason that this is really advantageous is, one, it can do blind searches, which is great. We can also observe to lower flux line limits compared to equivalent medium band imaging, where we don't get as much sensitivity, or slitless spectroscopy, and thus allowing a sensitive and clean selection of line emitting galaxies over cosmic time. Also, thanks to the resolving power of JWST, we can start to spatially resolve some of these objects, as has been discussed already in previous talk. And due to the narrow nature of these filters as well, we're looking at very small slices in redshift space, and so very good for clustering analysis as well as for studies of large-scale structure. So the motivation for GELS is specifically the H-alpha emission line, which has been talked about quite a bit over the last couple of days, a nice schematic of where you see a H-alpha emission from the pinwheel galaxy. And the reason we care about this is, as much as it's an indirect tracer of star formation, it's much less affected by dust compared to UV-based tracers, and in some cases gives a much more complete picture of star formation, particularly when we're looking at higher redshifts, cosmic and above. One of the things we also want to do is compare our sample selections using the H-alpha emission line to other star-forming galaxy samples, such as those based on UV studies, like Lyman break selected galaxies, and also build upon the previous work that's been done previously on the ground, so HISLs, which was also led by Edinburgh back in the early 2010s, but this was only limited to cosmic noon about redshift 2 due to the opacity of the atmosphere redward of the K-band. So just very briefly to go over the science cases that GELS aims to tackle. So building upon the previous work on the ground, there's a bunch of science cases that we hope to achieve from this cycle 1 data that we've managed to obtain from JWST. So the first one, which I work very closely with, is looking at the first blind search of H-alpha emitters at redshift 6. So here we've got a luminosity function showing H-alpha luminosity function from the local universe up to cosmic noon, and a kind of preliminary kind of predicted LF that we get from the kind of proposal that we put forward, and then also translating this and integrating the luminosity function to then get the cosmic star formation rate density at redshift 6. So work I'm doing is trying to get more of a handle on the properties of these galaxies so that we can then make accurate measurements of the LF and star formation rate density. Another project that's going to be ongoing at some point soon as well is constraining the faint end of the luminosity function at cosmic noon. So from the ground, we've done a pretty good job getting the bright end of it, but with thanks to JWST and its sensitivity, we want to go fainter in luminosity space and really constrain the faint end slope, which will have a massive impact on your measurement for the star formation rate density. As mentioned about the resolving power from JWST, given that the H-alpha emission line traces ionized gas, we're able to spatially resolve this both at cosmic noon and epoch of ionization, thanks to JWST, and get down to sub-kiloparsec scale resolution as well. And of course, we don't just select H-alpha with these narrowband studies, but we also select other emission line galaxies across cosmic time, a few listed, including the Passion lines, N02 and O3. So we have tested this, and it does work. We do see line emission galaxies, so just kind of tested to show how this is working. If we look at the F44 broadband image and compare it to the 2 narrowband images from JWST at 4.5, 4.6 microns, we see where in both cases you pick up emission in the F44, more booming emission in the narrowband, but then complete dropout in the adjacent narrowband right next to it. And what we have here is an H-alpha emitter at redshift 6 and an O3 emitter at redshift 8. And the nice thing about this sample is that these 2 galaxies were picked up by our primer survey in Edinburgh as 2 separate objects, but when we measure the SEDs of both objects, we see that they're exactly the same redshift. So the fact that we're able to resolve structures this well at such high redshift is just a taster of what's to come with selecting different line emitters across cosmic history. So this is the first sample of line emission galaxies that we've got so far, which we're really happy with. It's got a lot of work that's gone into this. And the thing that I'm really excited about is that, yeah, we've got a H-alpha emitter sample at redshift 6. It works. This is something that is not been done previously. Although a few surprises along the way as well, so unexpectedly high numbers of O3 emitters, which we think are likely contaminants. So a bit more work that needs to go into the final sample, but we feel quite robust in what we've managed to achieve at redshift 6 with the H-alpha emitters, which I'll go on to talk about next, because this is part of my thesis for my PhD, is kind of focusing on this regime. And one of the things we want to do first of all is kind of get a handle of these galaxies, looking at their physical properties, so that we can then measure the luminosity function, star formation rate density, and also compare against samples of UV and H-alpha. So looking schematically at some of the images, these cutouts is thanks to Rachel Cochrane, we're able to actually isolate the H-alpha emission by taking the difference imaging between the narrowband and broadband and see the kind of central kind of star formation taking place here. But what we also see when we look at the other wave bands is extra rest UV and optical continuum components, as well as the fainter UV that you expect at the locations of H-alpha. For this middle row, we reckon we're actually looking at a completely different galaxy, either in the foreground, most likely the foreground or the background. These extra features here are examples of like you're very close in the sky. So this is where work looking at resolved SED fitting of these galaxies, as well as the kind of ionized structure, is going to be really crucial moving forward. So just a nice preliminary result right there. One of the things that we want to look at in order to constrain some of the properties of these galaxies is looking at the beta slopes. And so here I've measured their beta slopes as a function of their uncorrected H-alpha star formation rate, just to kind of get a first pass to see what are the kind of UV slopes and hence a handle on the dust looking like for these galaxies. And what we notice is that our weighted average, if the beta values are pretty flat with H-alpha star formation rate, but also that the average value of the weighted average value of the beta slopes is quite a bit redder to those that were selected using the Lyman break techniques when the Wide Field Camera 3 went onto Hubble, and we had this flurry of papers in the late 2000s, early 2010s, trying to find really blue Lyman break galaxies. So we're here, what we're seeing is that we're actually picking up a different population of star-forming galaxies that have been missed, most likely from previous surveys, due to the fact that they're probably much dustier. The first pass of the luminosity function, so here I've replotted what has been done at cosmic noon. And the red points is what we predicted looking at the previous plot. And then what I've managed to do is take her sample of H-alpha emitters, bin it in luminosity space, and then also considering those detected in both narrowbands separately in the gold and the silver. I fit a Schechter function to it and got my first preliminary luminosity function, which is a great win at this point. A few caveats though. So first of all, we still need to account for completeness at the faint end, but in order to do that, we need size distributions of these objects, seeing as that they're very resolved. So we need to figure out, what size distribution of these objects there are in order to run completeness simulations to correct at the faint end. And also, given that we still need to delve deeper into the dust properties of these galaxies, there's a few assumptions that have gone into the ALF, so an assumed value for the dust attenuation on the line itself, and also assuming that L star is approximately constant from cosmic noon to redshift 6, which is what we see based on UV studies, though this will be much more informed when we get more accurate properties of this sample going forward. And then here we've got our first, when we integrate that luminosity function and convert it into a star formation rate density plot, we finally get our redshift 6 point, which is brilliant because it means we're starting to populate this high redshift space. So unfortunately, no 0 to 20, but we've at least got 0 to 9, going a bit beyond and not just UV-based measurements. Though I must say that, as you can tell by the error bars, this is very much a preliminary estimate, and there's more work to do in this front, but it's really exciting first results going forward with this survey. So future work in summary. So where are we at and where are we going? So as I mentioned earlier, there's a bit more work to be done before we can kind of get more concrete conclusions. So our kind of size distributions and morphologies of this H-alpha sample has been led by Harry Stevenson at Lancaster University, as well as clustering analysis and completeness simulations carried out by Catherine Hale at Oxford. And then I am currently trying to relate the UV and H-alpha properties of this redshift 6 sample, along with some informed SED fitting to get a handle on the dust properties and also probe the connection to potential UV biases with my sample. And then together with dust properties, size distributions, completeness simulations, I hope to more accurately measure and get a more finalized version of the luminosity function, star formation rate density, and of course the consortium itself is still trying to drive forward the other science cases looking at other emission line galaxies over cosmic time, luminosity function, redshift 2, etc. I would also like to draw attention to the fact that we've also got an approved ESO large program led by Mark Swinbank at Durham, which aims to cover the whole of the GELS area with Muse spectroscopic follow-up, which will be public. So if there's anybody that's interested in aiding our collaboration with this, please do get in touch with Mark. And it'll be really nice, as you can see, we can pick up other emission lines corresponding to different redshifts. So for example, Lyman alpha with H-alpha at redshift 6, which is exciting. And of course, we're looking to the future and future proposals. We're hoping to use more narrowband filters from JWST to cover more redshift space, to fill in the gaps in cosmic time, but also increase the depth in the area as well of the imaging to go brighter and fainter luminosity dynamic range. And with that, I will leave you with my summary and just reiterate the last point that we've got some exciting new results, but there's still plenty more work to do. I'm really looking forward to see where this work goes. Thank you very much.
Thank you very much. Okay, what questions do we have for Corey? Any questions? Yep.
This is lovely. So you kind of intimated that we might have been missing a lot of the star-forming galaxies previously at redshift 6, but then when you had your point on the Dow diagram, it looked like it was kind of right on top of what we had before. So do you want to comment on that?
Yeah,
so
I think what the UV studies do is they do a very good job at making statistical corrections to their sample at higher redshift, such that they can kind of correct for these biases.
So they actually did it right.
Yes, but in terms of looking at the kind of individual properties such as star formation rate, stellar mass, and then this kind of distribution function with this plot as well, that's where we might see that there's definitely differences in the selection biases when you select on the emission line at H alpha compared to, like, for example, Lyman break or other UV-based selection methods.
Okay, great, thanks.
Since you are on this plot, can I ask a question? Is that plot the data point corrected for attenuation, dust attenuation?
Yes, so this is currently assuming a median. So when we compute the luminosity function, we're assuming a median dust extinction value of 0.4 based on an extrapolation of the UV studies currently, which is why getting more accurate dust properties of these objects is really important, because then we get a much better handle on the dust in the LF that we then integrate to get this cosmic star formation rate density plots. So we do actually, based on our method, expect to be quite well in line with the UV-based studies, that there's room for wiggle room for when we do kind of get more direct measurements of the dust.
Thank you.
Any more questions? If not, let's thank Corey again. Thank you.
Thank you.
Let's see. Testing. 1, 2, 3. Can everyone hear me? All right.
Excellent. Thank you so much. So next we have Ali Kostovan, who's going to be talking to us about extreme emission line galaxies from low to high redshift. Take it away.
Alrighty. Usually I always mess up with these clickers, so let's see how well I'm going to be able to do this. Is this? There we go. All right, so I'm the person who's in between you guys getting lunch. So hopefully I get you guys interested in extreme emission line galaxies, or at least remotely interested by the end of this talk, and then we get to have food. All right, so extreme emission line galaxies. First thing, what are they? Extreme emission line galaxies are a subset of primarily star-forming galaxies that are characterized by strong nebular emission. Now, what I mean by strong nebular emission, I'm referring to galaxies that have emission line properties and emission line strengths that are even sizable enough to dominate broadband filters. So you will see the SED of these galaxies and see a nice blip in one of these broadband filters that will be indicative of high equivalent width systems, really strong nebular emission line features. And people have been studying these types of extreme emission line galaxies for quite some time at low redshift, where we're primarily finding that they are low mass, they're quite bursty. So this is for blueberry galaxies, which are a subset of extreme emission line galaxies. They typically lie well above the main sequence and are also quite compact in rest frame UV and optical sizes. And couple that with their elevated star formation rates, it implies that their star formation rate surface densities are also quite high as well. And that they also are quite low in metallicity and have energetic ISMs. Some populations of these extreme emission line galaxies are also confirmed Lyman continuum leakers as well, that you have Lyman continuum escape in these sources, and they also have elevated ionizing photon production efficiencies. All of these components put together are similar to the typical properties that we would expect in high redshift galaxies, which the JWST is also now finding. But one thing is, these types of sources, however, as they are ideal labs for us to do high redshift science in greater detail in the low redshift universe, they're also quite rare, and that's primarily due to the fact that equivalent width distributions are quite narrower as we go towards decreasing redshift. So if we can find these types of sources, but at somewhat higher redshift, we can still do these, for example, at intermediate redshifts, we can still do high redshift science, but in greater detail in a lower redshift universe. Now, before I continue, I do urge the caution on how we define some things that are extreme. So in past studies, the way that we would look at extreme emission line galaxies is by basically saying anything above some equivalent width threshold. But the problem here is that when you're designing that sample, you may select things that actually have typical equivalent widths relative to galaxies at a fixed stellar mass. While at the same time, at higher masses, you can get those rarer objects that could be then characterized as extreme relative to the typical population of emission line galaxies at that given stellar mass. So that's one caveat to keep in mind, that when we want to then look at extreme emission line galaxies, we basically want to look at things that have high equivalent width relative to galaxies at a fixed stellar mass. So that being said, at RIT, a group of us, including myself, we're working on a project called Cosmos Spectroscopic Archive. And this involves taking a lot of data that has been observed within the cosmos field by multiple observatories. As we were sifting through the data, looking at all the reductions, we came on a peculiar source that we were not expecting. And what happened was we were going through GMOS data, and we found this one interesting source that had really strong O3 H beta emission, but also had a detection of the auroral 4363 emission line. When you see something like this, it's a telltale sign, okay, we're looking probably at a very low metallicity system, that we have the O3 4363, and the bright O3507 and H beta, that also tells you that this could potentially be a quite energetic galaxy in terms of their ISM conditions. And when we did detailed spectrophotometric SCD fitting, we found that this source is actually quite bursty. It has very high specific star formation rates and a mass doubling time that is on the order of about 7 to 8 million years. And you can even see within the broadband photometry that there's this clear bump that signifies that there is a high equivalent width emission line feature in there, which is the O3 H beta line. Now, how extreme is this one source, which we call ELG1002? That was just the object ID number within the mask. So taking into consideration the equivalent width stellar mass anti-correlation, comparing this source to typical redshift 0.8 galaxies, this one source, which throughout this talk is this blue star right here, it's 30 times higher in equivalent width compared to galaxies of similar mass at similar redshift. And in that respect, this is actually quite rare source. It's an outlier compared to the typical population of O3 emitters that you would find at this redshift and stellar mass. And not only is it just an outlier, it's actually quite comparable to even redshift greater than 6 measurements, emitters that are being found with Eiger and other JWST programs, and is also comparable to known Lyman continuum leakers at redshift 0, and even blueberry galaxies, which are really low mass bursty star-forming galaxies in the local universe. And just aside, this is at about 4,200 angstroms in rest frame O3 H beta equivalent width. When we look at the ISM properties of this galaxy, we find that they have quite energetic ISM conditions traced by the O302 indicator, or line ratio, and it's comparable to high redshift sources that we're also finding with JADES, with SEERS, and various other JWST programs, and comparable to low Z analogs of high redshift galaxies. Now, when we look at the gas phase metallicity, which is directly measured from the O3 4363 line, we find that not only is this source quite metal poor relative to the mass metallicity relation at redshift 0.8, but it's actually also quite comparable to redshift greater than 6 galaxies, as the ones shown here from Eiger, suggesting that this galaxy is quite comparable to those high redshift sources in terms of their equivalent widths, stellar masses, ISM property, and gas phase metallicities. Now, you may think that, okay, well, what was driving this really strong O3 H beta emission? Could it just be, an AGN that's pretty active? Well, from all the evidence that we can see, that doesn't seem to be the case. When we look at the mass excitation diagram, BPT, this source falls within the selection area that we would consider to be primarily star-forming galaxies. We find further evidence for a lack of AGN by looking at X-ray observations from Chandra and XMM. We don't see any emission associated with the source, and we do not see any broadline features within the optical spectra, all indicative that this source has its emission lines primarily powered by star formation activity. So now we want to understand, well, how is a star formation actually occurring? So we can do star formation history modeling. With Segal, that is using parametric star formation history models. And from what we learned from that, in our initial detailed analysis of this and of the SCDs, was that this source has a very intense burst of star formation activity with a very short mass doubling timescale. Using backpipes, we can do non-parametric star formation history modeling to get a better understanding of what star formation was like in this source. And doing that actually results into something like this. And this is actually the default plot that spits out from bagpipes. It's not an empty plot. It basically shows that between 3 to 10 million years, there was just a sudden burst of star formation activity. Now you can say, okay, well, maybe it's an outshining effect problem. Your photometry is dominated by young stellar populations that were formed in a recent burst. You're missing the older population. But take this into the context of, well, does this even match the framework of our understanding of galaxy formation and evolution? And for that, we look at simulations to find analogs of these types of sources. And indeed, we do find things that are somewhat reminiscent, where you have hardly any activity, and then all of a sudden a big burst of star formation activity. And from what we can tell within these analogs within Illustris, it seems to be that these are residing in really gas-enriched subhalos. So you need cold gas to feel that star formation activity. So if it's within these environments, perhaps ELG1002 is within those gas-enriched halos and has the gas in order to feel this intense burst of star formation activity. However, you would expect that then it should be like in an environment, for example, like a filamentary structure, where you can have these cold streams of cold gas to fuel that activity. But this source, looking at the variable spectroscopic data that we have, is actually quite isolated. It's within a region that really doesn't have high local number densities. So it's quite unclear exactly then how this star formation activity is essentially enabled in this galaxy. Now that being said, the last thing I would say about this one source is it also has ionizing properties that are quite reminiscent to even some of the most high equivalent width and also highest specific star formation rate sources that are currently being observed with JWST at redshifts greater than 5, greater than 6. And really to get a full understanding of the rest frame UV properties of this one source, we really need resolved and deep UV coverage of this object. And that would require going after HSD costs, and also a shout out for HWO if we can get that as well in the future. So the last part of the talk that I'm going to quickly go over is, can we find these types of sources, a galaxy similar to ELG1002, at higher redshift as well? So in this case, we've used Cosmos Web data using the NIRCam filters, and we were looking for galaxies that could potentially have a strong emission line feature that would dominate the broadband filters, the NIRCam filters. And indeed, we do find these types of sources. So this is ELG1002, and we do find these sources that have really high equivalent width and also high ionizing photon production efficiencies. And just to give a glimpse of what some of these sources look like, here's one in particular that has about almost 5,600 angstroms. You see a nice blip right here that's corresponding to the O3 H beta emission. And that was at redshift 2. At redshift of about 7.4 in F444W, you also see a blip that could potentially be a really high equivalent width emitter as well. So these sources do exist at such high redshift, and implying that they're quite bursty as well. And you may say, okay, well, those are photometrically selected objects. Well, we did go after one of these objects as a filler in one of our Keck programs, and we did confirm for this one redshift 2 source, where we see this nice blip in the NIRCam photometry and also ultravista photometry as well, that we have H alpha and O3 emission for the source. And these are the cutouts for that object as well. So this source was selected primarily based on the F150W emission. And when we compare the emission line properties of this source from the Mossfire spectra to what we're getting with Seagal, it's actually quite comparable to one another, meaning that Seagal has done a pretty good job of tracing the emission line properties to give us an estimate of what conditions are like for this source. And further work is still on the way for this object as well. So the last thing that I will mention is, what are the prospects of finding these types of galaxies in larger, wide, and deep surveys with Roman and Euclid? So Euclid has launched, it's on its way for science to come out, and we have Roman in the very near future. And this work was a project that I did with James Rhodes and Sangeeta Malhotra, where we were trying to model the H alpha equivalent width distributions using a forward modeling approach to gauge a range of equivalent widths and stellar masses that would be observed within Euclid and Roman. And what we come to the conclusion of is, yes, we will find sizable numbers of these types of emission line galaxies in such wide and deep surveys with Roman and Euclid. So I'll leave the summary slide here, but the one thing that I will really point out is ELG 1002 was found within archival data. As my work in the spectroscopic archive for the Cosmos team has been progressing, one of the things that really has popped out is as we're getting more data when it comes to Euclid, Roman, a lot of these ground-based observatories that will be online in the near future, there's going to be a lot of data for us to work with. At the same time, we have lots of archival data that are just sitting within the archives that could still be used for great science. For example, this one source that by accident we found as we were going through the data. Thank you.
Thank you, Ali. We have time for a couple of quick questions.
Hey, thanks, Ellie. Nice talk. You found these analogs in Illustris that showed this sudden burst. I'm curious if you looked at the fate of those. Like, what did they progress to after the burst? Did they become more normal star-forming galaxies in their growth, or did they quench themselves with a big burst, or did you look into that at all?
Yes, so that was very preliminary work, because what happened was I was looking for these types of sources. And I was hoping to use the star formation histories to actually input that into Seagal in order for us to actually use that as a star formation history for the SCD fitting. The only problem was that the time resolution wasn't that great. And I know that there is a higher resolution. I'm not an expert when it comes to simulations. I know there's a workshop for Illustris I'm definitely going to be attending. So whoever you are leading, I'm super excited for that. To answer your question directly, I haven't checked to see what the descendants of these types of galaxies would be. It will be really cool, though, to see if, after these intense bursts, do these sources just, die? If, it uses up all of its gas and just ends up being, dead, quiescent, maybe dwarf galaxies, because these are very low mass as well.
Thanks.
Any more questions? If not, let's thank Ali again. So now we have a discussion session. It's going to be led by Janice Lee. And then before you eat, you need to take your photo. So we'll be heading outside.
Okay, I'm in the way of this large audience and lunch, so we have to make it fun, right? So I put together some slides with themes, and then also a few slides about what the heck this is, because it's been mentioned a couple times. But for the sake of discussion, can we turn that off for a sec? I want to see if people have any burning questions that they want to bring up that they haven't asked yet during the talks, because there are a lot of themes. I think it's really amazing that We're at the end of 2 days, a day of discussion on star formation and feedback. We have people who study Milky Way objects, nearby galaxies, all the way out to 500 million years just after the Big Bang, and we can keep them all in the same room without subpopulations fleeing because we're now all being able to look at star formation at these small scales throughout the universe, and that is just simply amazing. And that means that we all have things to learn from one another. So I have thoughts, but I thought I'd open it up to the audience first to see if there are any big topics you wanted to discuss. And the slides are really just back up here in case everyone just falls silent. Rachel.
Something that
New Jersey in the house.
New Jersey in the house. Something that came up yesterday, and we didn't hear much about it today, is dust yields from supernovae. And I think that there are recent observations from JWST, for example, that are constraining those. So I just wanted to put that out there. And it sort of connects to this theme that did come up a lot yesterday of understanding stars and stellar populations and how important that is to understanding feedback. So that's just one more piece that I haven't really talked about yet.
The little I know about that is that there's a large uncertainty in the yields. Can anyone speak to that?
So is this recorded?
Actually, we can shut it off because...
Okay. And from the depth of my ignorance, I can report what I heard last month at another conference that was more devoted to dust. And apparently one of the biggest uncertainties, as Janice mentioned, is that there is a very difficult time in trying to separate what is being produced by the supernova versus what is pre-existing. So separating the two is very challenging, and I think that's what may account for the large uncertainties that are still floating around. Of course, if there are better experts than me, they can speak to that.
And how do uncertainties in the dust yields from supernovae affect the feedback models? On the simulation side?
Well, I mean, from the simulation side, what we do see is how much dust there is a very strong indicator of how, because the dust acts as a great source of opacity for the radiation, and therefore can transport a lot of momentum to the gas. So the more dust there is, the better it is for the feedback. So yeah.
Yeah, especially for early feedback, huh? Mm-hmm. Because as we've heard, one way of constraining the types of feedback that are important at different times is through comparison to different age stellar populations. And there have been a large number of studies that are showing, including some of the works that have been cited in several of the talks and Siobhan's, that feedback has to act early before supernovae start going off. And that's below 3 million years. So what is that? Radiation pressure. So we had
I just want to add to that dust also plays a role as a heating when it coupled with the UV radiation. And if there is no dust, and then we need another heating source, which probably also relate to the maybe. So I mean, I think another thing that I may come up with is cosmic ray ionization, but because that's also related to the supernova, so it may also come later. So then maybe it's just really the post-ionization that's really heating up. I think that's so I think it's related to the orders. If the dust came in, I think the dust heating is important, but then If it's not, then there must be something else. Yeah.
Can I ask a question? So I'm slightly confused by what I thought was your statement, but maybe I misunderstood. So how is dust yields entering into early feedback? I am confused by that statement. Okay, maybe you can answer. Sorry.
It's great. Discussion on this side of the audience, too.
I can try to summarize. I mean, I think.
Go ahead, Rachel. Go. Where is the mic going? All right.
I think the question you're asking is how does it directly play out, because there's different time scales. But I guess the more broader point is the dust yields sort of set how much dust there is in the galaxy overall, and so the star forming regions inherit that dust, and so that sets the initial conditions in which star clusters are formed. So future generations, I think that's at least from my point of view.
Hi.
So I guess I would want to know, with pre-existing dust, we should expect that larger dust grains are destroyed when exposed to high temperatures or the energies of a supernova. So what is the actual output in terms of grain size? Like, how soon should we expect larger grains to start reforming after a supernova? Because that does impact the radiation pressure feedback.
Grain size distribution. Can anyone comment on that? I mean, we're talking about dust as one constraint on feedback models, but of course we can also open up the discussion to what are the best predictors or constraints, observational constraints on feedback models. We can talk about dust, we can talk about other things. Up here? Here.
So this is not my expertise yet, but I'm entering this formation of dust side as well. So I'll be calculating nucleosynthesis yield of elements using the same supernova model. We are calculating dust yields as well, following the dust production within supernova ejecta. And that's the production from the very small scale. And after the ejection, dust should glow, changing the size evolution as well. So that's the ISM physics, and we actually don't know very much about it. That's still small scale compared to galactic scale, and then the feedback will be blown away at some point. So it's just a comment on that. It's highly uncertain yet, but committee should be working for that.
Other thoughts? I mean, Linda.
Yeah, I was thinking this yesterday, actually, and I just remembered it again. So, does feedback change with metallicity? From the massive star aspect, I would expect it to, because as you go to high redshift and low metallicity, you've got two, competing effects, if you will. The mass loss rate goes down because of the low metallicity, and you also have a denser medium surrounding the cluster or whatever, where the wind has to get out. So I don't see, it must change. Early feedback must be different because of those effects.
Or feedback free.
Yeah, exactly. Yeah.
How does feedback change with metallicity and over cosmic time?
So I was going to ask a similar question, but I can actually comment on that. So there are many metallicity effects. Winds are line driven, and so metallicity directly impacts your ability to get feedback from stellar winds. But you can also get delayed supernovae feedback because low metallicity stars are more likely to have supernovae happen at lower stellar masses. So there's a time delay in your supernovae feedback, so you actually get less heating and mechanical feedback. And so then you also get less dust. And so you're going to have a lot less feedback and a lot of capacities because of that.
Sorry, may I ask a follow-up question? So you can actually explode the stars to a much lower mass, but what about the first massive stars that can explode? Is that comparable to between high and low metallicity, or do you have a difference in there too?
Okay, yeah, so that's good clarification. So what I meant was that the mass at which supernovae start to happen is lower. So your higher mass stars don't go supernova, they just go direct collapse. And so you don't get the mechanical feedback that you would expect otherwise. I would refer you to Jeckman and Uwe. That was a paper that came out earlier this year that explored that in detail.
Other comments on feedback and the dependence on metallicity?
Yeah, so I'm a little confused about radiation feedback. And I thought the early effects were mostly from H2 regions, which sometimes people use as a radiation feedback, and now I'm hearing that radiation pressure dominates. But I didn't think that radiation pressure on dust dominated, say, cloud destructions or early feedback. I thought it was the H2 region, the ionization photons. In that case, I would think low metallicity, although the winds are small, there'd be less line blanketing. So there'd be more UV coming off a given solar mass, a given star. Moreover, in these H2 regions, you often see the wind cavity inside. So it's a multiple structure even before supernova. H2 region is doing a lot of clearing, and then the hole from the fast wind inside of that. But still, it's the H2 region pressure that, so eventually maybe a radiation pressure, or in tiny embedded sources, embedded before the ionization comes up, radiation pressure on dust would be important.
Yeah, does someone want to comment on the difference in importance in the various feedback mechanisms? Yep.
Yeah, you're right. For typical for H2 regions you see in the Milky Way, that's probably right in that it is the thermal pressure from the photoionized gas that drives the H2 region. But if your clouds are very compact and your escape speeds from the clouds are higher than the ionized gas sound speed, then there's no way the thermal pressure can do anything. So in those cases, so I think the way to think about this is that the conditions in embedded H2 regions is essentially the whole cloud for higher redshift, or dense compact sources. So in such conditions, it is the radiation pressure on dust that drives the H2 region. And this has been shown in a lot of work. But another effect related to the thermal pressure of the photoionized gases at lower metallicities is that if that feedback route becomes important, the photoionized gas is hotter at lower metallicities because there's no cooling from metals. So that acts in a positive direction for feedback in that sense.
Okay, any comments on that? Or else I will say a few words about this HWO thing that doesn't seem relevant to us because of the title here, but yep.
I just want to point out that there are a couple of questions on Slack.
Oh, okay, that's great. Are those the first questions on Slack this conference?
Yeah, so we've got one question from Bina Mina. How do you define star-forming hierarchy? Do we have a consensus on the physical process behind the observed hierarchy in star-forming regions, which is usually found as compact, denser young stars residing inside the older, lower density populations, and how is this formed?
Wow, that is a huge topic. The star formation hierarchy and how we define it and what it means and the timescales for dissolution and how it relates to the compact clusters. Does anyone want to give a stab? One talk? Well, there are a lot of people in the audience, yeah?
Well, you gave such a good review, you should comment these hierarchies.
Okay, so from the bottomless pit of my ignorance, I will say that the little we know about hierarchies, and there are many works dating back to the mid-90s try to actually characterize that, looking both at two-point correlation functions and also age separations as a function of physical separation, so there are different methodologies, and they all point at the fact that you have that the two-point correlation functions remain shows clustering all the way to about a few hundred parsecs for ages up to about 100 million years, give or take. And then whatever population you define is actually merges into the field of the galaxy. And this time is this scale is actually determined. Well, there is actually a beautiful paper by Shian Menon. Where is he? There you are. Your paper that shows that is actually correlated with the tumorin length in galaxies. So showing that practically gravitational instability is what determines how clusters. So why am I speaking? You should have done it.
And I mean, there are a lot of other people in the audience too who have done work on star formation hierarchies and associations, but I'm not going to put them on the spot.
Yeah, Kitty Grash is also one.
Yeah, if you can respond in the Slack to the comments, that would be wonderful. So what's the second question on Slack?
Yes, the second question is from Yumi Choi. How are we doing with star formation rate measurements? With JWST, we now have more variety in star formation tracers, but they are tracing different timescales at different spatial scales. Do we need to revisit the empirical star formation rate relations?
Wow, that is another whole conference. But I mean, this is one of the things I had on my last slide. We have to be careful, right, when we're using any kind of star formation recipe. It depends on the assumptions underlying the recipe, or even if you're doing some kind of SED fitting, right? We've heard a lot about the star formation histories under the hood, right, that can change what we measure about different physical properties. And, you know, to Yumi's point, when you get to larger and larger regions, right, you're averaging over many, many more individual star formation events. So you're smoothing it out. But even then, we heard about how, you know, the parametric modeling that we've been doing, the assumptions of different parametric forms of the star formation history is leading us astray. So I think we do have to be, I don't think we require a huge reevaluation. I think all of us just have to be really careful when we're trying to measure the star formation rate, to understand the assumptions behind the calculations that you're doing. What IMF is it based on? What metallicity? What star formation history? The underlying stellar evolution models, right? They're going to change as a function of metallicity locally and at higher redshift. I think we know a lot about how to measure star formation rates. We just have to be careful. I have 1 minute before everybody goes to lunch. I just want to see raise of hands. So how many people actually know what Habitable Worlds Observatory is in here? That's half the audience. All right, 60 seconds, and please come talk to me at lunch because I'm on the Habitable Worlds Observatory science team, and it's a big part of my work here at the Institute. Super Hubble. This thing is not only going to find exoplanets and look for biosignatures, but it is Hubble on steroids. Imagine all the things you cannot do with Hubble now and increase the size of the aperture 2, 3, 4 times. We are looking for science cases. There will be a talk from Jason Tumlinson on Thursday at 1:30, but I've already talked to many of you because you're exceeding the limits of what we can do with Hubble. And in the next 3 months, we're going to be drafting science cases in order to inform the capabilities of this fabulous next generation observatory. So please come talk to me if you're interested, and then look forward to the talk on Thursday to give you more background. Okay, have a great lunch.
Remember, everybody, the photo before lunch.
Sorry, photo. Go outside on the steps.
On the steps. Thank you, Janice.